Discretization method. So we're going to continue our discussion of boundary value problems. And if you'll recall, a boundary value problem is exemplified by a second-order ordinary differential equation whose solution is a function prescribed at the endpoints of the interval of interest. And last time we talked about a shooting method to solve this. Here we're going to look at different ways to solve this type of problem, including a modification on the shooting method. So this approach that we're going to discuss first is the discretization method, and it's a completely different approach than the shooting method. This one is based on a direct discretization of the differential equation. So to solve this, and again, x double prime is a function of t, x, and x prime. It could be all three, it could be one or two of them, but it's some combination of those. And we know the initial condition at A is equal to alpha, and the end condition at B is equal to beta. So we start by selecting a set of equally spaced points, t0 through tn, on the interval AB, and we assign each t sub I equal to A plus the interval IH, and H is B minus A divided by the number of points. So they're equally spaced out points. Step 2 is approximate the derivatives using the central difference formula. And you'll remember those no doubt from Calc 1. And then the problem gets transformed into the one you see in Step 3. In this bottom formula, the approximate value of x of t sub I is denoted by x sub I. This is usually a nonlinear system of equations with n minus 1 unknowns, x1, x2 through xn minus 1. We know x0 and xn in this case. Because the fact that f generally involves the x sub i's in some nonlinear way, the solution is seldom easy. Of course, we might get lucky and get a linear system, and let's look at what happens in that case. So here's the linear case, and this occurs where f, which is the second derivative, is equal to a function of t, x, and x prime, and it's equal to u of t plus v of t times x, which is its original function, plus w of t times x prime. From there, we can figure out a, d sub I, c sub I, and b sub I, and then transform this principal equation into a sub I times x to the I minus 1 plus di times xi plus ci times xi plus 1, and set that equal to bi. We know the equations for x0 and xn. The other ones, x1 through xn minus 1, can be written out in this format here. And this system can be written in a matrix format, and it's actually a tridiagonal system. Now, the tridiagonal system is really good for us, since we can store and solve these problems more efficiently, as seen way back in Chapter 2 if you took CS 407. If it has some leading zeros, then we might have to use scaled partial pivoting, but this is pretty much a best-case scenario for us. The text covers a specific numerical example that we'll get to in a few minutes, along with the pseudocode that you can find on pages 515 to 516. This function obviously uses the tridiagonal routine from section 2.3, so you'll need to have that coded up. The results are fairly good and have errors in the range of 10 to the minus fourth for each step. Now let's take a look at how the shooting method would work in the linear case. The linear 2-point boundary value problem, again, is x double prime of t is equal to a function u of t plus v of t times x plus w of t times x prime. We have x of a is equal to alpha, and x of b, the endpoint, is equal to beta. Now, the shooting method requires us to solve an initial value problem and interpret x of b as a function of z. We call the function phi and seek a value of z for which phi of z is equal to beta. For the linear problem, phi is a linear function of z. So that's good because we only need to solve the problem with two values of z to determine the function precisely, because it's a straight line. It's a linear problem. So perhaps the simplest way to implement these ideas is to solve two initial value problems. And we basically have x double prime and y double prime. With x of a equal to alpha and y of a equal to alpha, we have x prime of a equal to 0 and y prime of a is equal to 1. The solution to the original 2-point value problem gets transformed into what you see at the bottom. Now, in the computer realization of this procedure, we need to save the entire solution curves of x and y, and those can be stored in an array or a vector or whatever data structure you're using to do this. The procedure looks at the same numeric example we use for the discretization method. The pseudocode can be found on pages 518 to 519 of the textbook in section 11.2. This function uses the Runge-Kutta method, which is found in chapter 7, specifically section 7.2 on page 315. We also need to do some variable substitution to combine the two sets of equations into a single system of equations in order to run that. The results for this routine actually have lower errors than the discretization method. So let's take a look at that problem so we know what that problem is and why the author of the textbook selected it. The numeric example here is x double prime of t is equal to e to the t minus 3 times sine of t plus x prime of t minus x of t. x1 is equal to 1.0973741 and x of 2 is equal to 8.637496661. This example is used because the closed form solution is actually known to be x of t is equal to e to the t minus 3 cosine of t, and you can differentiate that twice to see that the result actually works. We can use the fact that we have the known solution to check the results of the routines. So how does mathematical software deal with this? Well, MATLAB, Maple, and Mathematica solve these problems in various ways. MATLAB and Mathematica produce numerical solutions to the boundary value problems and plot the solution curve. Maple can solve the two differential equations and combine the solutions in an analytical manner, and it can also produce intermediate results. They do not produce the solution to these problems instantaneously. There's actually a lot of calculation going on behind the scenes. The other thing to note is sometimes boundary value problems have no solution despite having smooth coefficients. And again, the authors refer you to the supplemental material in the bibliography if you're interested in what conditions apply to having a solution there. As always, thanks so much for watching.